Today I will present some joint work with my supervisor Fernando, who is now at the Okinawa Institute of Science and Technology in Japan. We work together on this approach of quantum error correction with dissipatively stabilized squeezed cat qubits. And I think I have the honor of being the only talk on bosonic codes in this conference, which is much better than last year because there was none. So I guess next year it's just all bosonic codes. So I will spend some extra time getting this crowd here intrigued by bosonic codes. But before that, I want to kind of distinguish two types of quantum error correction. One of them is active quantum error correction, which is what everybody kind of is familiar with. We use many qubits to encode a single logical qubit. We then measure syndromes repeatedly, feed the syndrome information into a decoder, and use this decoder to correct errors on the fly. So this is hard. As we've learned in previous talks already, we need to measure syndromes. We're going to have leakage as qubits escape to higher levels. It's just a big mess. So another approach is autonomous or passive autocorrection. And it's a very different approach. It's a lazy approach because we want to engineer a system, an open system usually, which has a twofold degenerate ground state, and we want to use this ground state manifold to encode a logical qubit. And these are kind of classical ideas in the sense that you can think about the two-dimensional Ising model as a classical example of this, which is an Ising model where the bond detection will favor alignment, and the all-zero logical state is just all zeros, and the one logical state is all ones. If you want to go from one state to another, well, this will come with an energy cost of order n. So the bigger the system gets, the less likely it will become due to noise, right? So if there's some noise in the system, some small perturbation, as the ground state of the system is our logical code manifold, we'll just relax back into it while preserving our logical information. So that's a great idea. Now, bosonic codes are also nice if we think about active error correction, as they are offering some kind of hardware-efficient way to do error correction. Like we have seen before, there's a service code which will probably need 1,000 or 10,000 qubits per logical qubit to reach the error rates we want to achieve. But with bosonic codes, the idea is kind of to reduce this hardware overhead. But first, what is even a bosonic code? Bosonic codes is logical information encoded into the physical Hilbert space of harmonic oscillator. So this is kind of quantum information language or LC circuits. The harmonic oscillator really looks very simple. Everybody has seen it probably in their quantum mechanics course in the bachelor. And the Hilbert space is just this infinite dimensional Fock space. So it's much better than a qubit because we have infinitely more levels. We have this creation and annihilation operators. So the creation operator takes you up one level on the oscillator, and the annihilation operator takes you down one level. This corresponds to gaining a photon or a single excitation or losing a single excitation. And we can use this large Hilbert space to spread information in the Hilbert space, as we do with the service code, for example, by encoding bosonic codes. And the probably most famous bosonic code these days is this Gottsman-Kitaev-Preskel code, or GKP code, where we'll encode information in a superposition of position eigenstates. They're spaced along this grid, and because there's this difference in this periodic tiling, we can first detect and then correct small shift errors. So our single qubit, our physical single design, will allow us to correct for a single error, and then we have a lower error rate that we pass into, for example, a service code or a repetition code. Now, for the experts, for you, this is an infinite energy state. So that's something which is unpractical, and we're today at quantum computing theory in practice. So everything looks a bit more messy if we go to the practical picture of this. But what is important here, it becomes a weighted superposition of squeezed coherent states. And I highlighted the word squeezed coherent states, as that's something that we will come back to. I also show the wave function of now this physical state. And you see it has this kind of sine periodic structure, even though the periodicity is suppressed around the edges due to a Gaussian envelope that makes this finite energy state. But what is important here, the resolvability of the peaks is still high enough to kind of detect small shifts if they're just small enough. And recently, people have managed to prepare this state in experiments. And there's, for example, early results by the group at the ETH, who did it first, and now more recently, this claims by Yale, who have used the system to stabilize the GKP qubit, which lives 2 times longer than the best physical component of their system, of the experimental setup. So that's a well, that's a big message for Bosonic codes. They're the first to do this, actually. So that's great. But apart from this, what other Bosonic codes can we use? And especially, like, what kind of role does distributive stabilization play? Well, I want to give like a very small introduction at like how distributive stabilization works. And we can imagine like the most simple system is just a harmonic oscillator. We're now in the rotating frame, so there's no like quadratic Hamiltonian anymore. And we have a single linear drive, so we add a single photon to the system. And we're also assuming single photon losses, which is very natural. There's kind of like photons leaking out of the system. We can rewrite this Limbaladian as a single dissipator, which looks of the following form. And what is important is that the jump operator within this dissipator has a single state in its kernel. It will have like this single occurrence state, which some particular parameters, which kind of looks like this Gaussian blurry blob in phase space. And whenever there's some small perturbation to the system, we'll return back to the state. And well, definitely that's not going to be useful. We have only a single state. We cannot use to encode quantum information. But it illustrates this point, and we can look at the same model, just adding 2s at some particular spots, which is this 2-photon-driven distributive oscillator. So we're going to add photons in pairs to the system. We also assume that we're losing photons in pairs. Maybe that's not so natural, but that's not the point right now. The point is that we can write it in a similar fashion, and now like the experts will notice that in the kernel of the jump operator, there's going to be 2 states, namely the coherent states plus and minus alpha. They're both ground states of the system, and if we're in any superposition of these states, the system will conserve the superposition even due to small perturbations. And what you see here is the superposition of this ground state manifold, which kind of looks like a cat state, which some people of you maybe have heard about. And the cat state is like one of the first Bosonic codes I would think about. And it's great because it comes with this very nice error suppression properties. The cat encoding is we use this coherent state alpha as a logical 0 state, and we use the coherent state minus alpha as a logical 1 state. And then all these superpositions of them make up the other cardinal points on the Bloch sphere. What can we do? Well, if you look at what happens if you lose a single photon, which is like some people claim the dominant error for these systems, you would have a bit flip error. But bit flip error is actually exponentially suppressed in the size of the cat. So the bigger this parameter alpha, the less likely they become. And since this exponential suppression is small cat, so like a few photons, will actually like reduce you to a very small error rate. Of course, the cat is not perfect. And there's this kind of drawback that when you increase the size of the cat, the phase flip error rate will increase. And while it's kind of like easy to do these derivations and so on, I don't like it because I like to think about physical intuition. So I want to try to teach you about this a bit. And what I show here on the side are the Q wave function of the cat state and the P wave function of the cat state. So let's look at this top left plot first. It's a small cat. It has some particular alpha square root 3. So we're going to see 2 peaks along the Q quadrature. And a bit flip error happens when we cannot distinguish these peaks well. And you see if we increase the size of the peak, the resolvability of the peaks increases. Like they're much easier now to distinguish. Like you can make sure, like, well, if something is on the left, it's going to be associated to the minus or to the logical 1 code word. If something's on the right, it's going to be the logical 0 code word. But what happens to the Q quadrature of the cat state is, well, if you take the Fourier transform of this bimodal distribution, you're just going to get some cosine oscillations, which increase in frequency. So if we grow the cat in size, like the density of peaks in a certain interval or the resolvability of peaks will actually decrease. So you can understand this as a mechanism why there's some linear increase of phase errors, as basically the peak quadrature is relevant for the phase errors. Or like when we do some like error of distinguishing peaks there, there's going to be a phase error. So this was bad, and like people struggled with it, and we ask ourselves, how do we squeeze out more performance of the cat encoding? And actually, you just squeeze it, which I think was our realization, which we enjoyed a lot. And everything looks very similar. You notice that I have introduced this Hamiltonian before, and now I replaced the operator A with an operator B. And this operator B is now the annihilation operator for a squeezed photon. So instead of pumping photons in pairs to the system. We're going to pump in squeezed photons to the system. And we also want to lose squeezed photons. Now, this might be a bit more challenging to engineer, but that's something which I will also address. But instead of stabilizing coherent states as before, what we're going to stabilize now are squeezed coherent states. So similar to this GKP qubit, our code space manifold is now made up of squeezed coherent states, which have equal but opposite amplitude in terms of phase, but they have the same squeezing. And this brings us to the squeeze cat qubit. And similar to the ordinary cat qubit, as I like to call it, we have like this nice error suppression properties. Again, we find that we have bit flip errors which are suppressed exponentially in the size of the cat, but we're getting an additional term in the exponent, which depends on the squeezing parameter r. And as you see, it appears in a super exponential way. It's e to the r. So even like very small parameters of squeezing will suppress errors quite significantly, as we will later see with our numerical simulation. And still, there remains this drawback of linear encrates and phase flips. So you might think we haven't solved anything, but actually we have solved something, because if you look closely, the parameter r doesn't appear. So now you have two independent parameters, the squeezing and the size of the cat, which allow you to tune bit flip error rate and phase flip error rate kind of independently. But yeah, again, like it's not so obvious that the parameter r doesn't appear on there. So let's think about this again in this wave function picture. Let's start with a big cat and squeeze it. And the way we define the cat, what happens to the Q quadrature is the peaks just get sharper. They have the peaks at the same origin or same points, but the resolvability is still increased. So you can see that it's still easier to distinguish left and right peak. But as the bimodal distribution has the peaks at the same position, when we take the Fourier transform, the peak density in the peak quadrature remains the same. Like as you see, in the interval from -2 to 2, there's 5 peaks for both states, and only like the peaks extend further in phase space. In some sense, it also reminds you about this GKP state. You see these quick oscillations, just like a GKP qubit. And actually, if we would have an infinite squeezing, we would have a very bad approximation of a GKP qubit, at least in the peak quadrature. And that's something that's good to remember for the future. So while we do all these theory results, it's always good to check what happens in practice using numerical simulations. So, well, people told me that they have checked the slides. They didn't. There were results, okay. Yeah, it does very well. Okay. I guess single photon losses are too trivial for this audience, so we're just gonna go to like more general errors. We checked dephasing, which is like similar to qubit dephasing is also a problem. It does not appear. It's usually much less of a problem in bosonic systems. So we derived some analytical results and compared it with numerical simulations. And we see that, well, if you squeeze the cat, which is like the blue and the yellow colors, it will always perform much better than the unsqueezed cat, which is the red line. It performs so well that in this regime, we cannot even resolve the bit flip probability anymore. And as you see, well, we can look at this point where basically dephasing is not a problem. As you see, it's a straight line. By squeezing just by like 5 dB or a parameter of r equals 0.6, which is very easy to do in experiment, we gain about 6 orders of magnitude in the bit flip error rate. So instead of running your algorithm with like 1 million gates, you now have like 1 million times 1 million gates before a logical error would occur on your cat qubit, at least a logical bit flip error. So it's nice that it always fits well to the theory I've derived, but it also does better all the time. There's this other problem of thermal noise sometimes. So here we were able to derive analytical results, and everything fits well, and the same story applies. The squeeze cat qubit always does better, and does so by orders of magnitude in the bit flip rate. It's unfortunate that I couldn't show you the phase flip error rate today, but it remains the same. And that's like the important question. Like we can squeeze the cat qubit, and the phase flip error rate remains the same in comparison to the unsqueezed cat qubit.
I really missed something, and because you didn't give me the squeezing angle. Can I just understand the squeezing,
sure.
just because I
Yes.
can't interpret these results without that, sorry.
Sure. So before you had two current states, and now you want to squeeze so they become like aligned with the q-axis. We can look at these plots. Thank you. Yes, so you could squeeze in the other way, but then you would actually increase bit flip errors because, yeah.
Maybe another question related to things that might have been in the missing slides. Can you say what kappa minus?
Kappa, yes. Sorry, yeah. So kappa minus is the single photon loss rate, basically. Where kappa 2, well, it's this stabilization rate of the cat qubit. So we want to lose photons in pairs. And what is an important ratio for this qubit is kind of like the undesired dissipation, which is single photon losses, where there's a desired dissipation of two photon losses, or squeezed two photon losses. So we're keeping this like constant, while in this plot like sweeping the dephasing rate, kappa phi, on an exponential rate. And once this line starts to deviate from a flat line, we know it becomes relevant to this case. We're doing this because we cannot really derive any results for the analytical bit flip rate for single photon losses. Thank you for your questions. But of course, I kind of like tried to argue that everything is great and there's no problem anymore, which is of course not the case. And the case is that there's some vulnerability to oscillator nonlinearities. So what does it mean? We know that the qubit, it should be restrained to two levels, and we have some nonlinearity in the qubit so that it actually cannot be driven to the third level of the qubit. For harmonic oscillator, it's harmonic. There should be no nonlinearity in the oscillator. But usually there's some, because without nonlinearity, we cannot do any quantum computing. You can think about as nonlinearity as a resource for doing like non-Clifford gates, actually. So what we checked here is some specific form of nonlinearity, which is known as the Kerr-type nonlinearity, has the following form, and we checked it for the squeezed cat qubit. And while the ordinary cat qubit like is basically not affected by it on an exponential range, the squeezed cat qubit immediately performs much worse. Like the bit flip rate will linearly increase, which is not so great. But actually, that's kind of expected. And we have some qualitative explanation for this, and there are multiple reasons. On the one hand, we know that if we send the squeezing to infinity of the cat qubit, it becomes like the GKP qubit in the P quadrature. And the GKP qubit is very much affected by oscillator nonlinearities and dephasing, as has been shown in previous studies and also been discovered by Yale, for example. On the other hand, the cat qubit is stabilized by some Kerr-type Hamiltonian. So before I mentioned distributive stabilization, we want to design the dissipatives of the system so that a particular state is designed. But you can also have Hamiltonian stabilization, where Hamiltonian is such that if you the states lie in the kernel of that Hamiltonian, and it's exactly this Hamiltonian which will stabilize the ordinary cat qubit with some parameter alpha. If you multiply it out, you'll find that there's some Kerr term included. So if Kerr is small, it doesn't really affect the state, as this will just deform the state a bit, but it will not push it out of the code space significantly. On the other hand, since the squeezed cat qubit is the cat qubit but just squeezed, we would need to have some squeezed Kerr, which doesn't naturally occur in the system, and we would need to engineer it artificially, which is kind of a challenge. So that's kind of a reason, but there's a good thing, namely we can identify this threshold where once this like K in the system is small enough, but there's still a squeezed cat qubit, which will outperform the ordinary cat qubit. And in general, you find that the K that you can allow in the system is bigger for squeezed cat qubits than for GKP qubits. Because you could say, well, if I have to get rid of any type of nonlinearity in the system, I might directly go to the GKP qubit. But no, we argue that there's some intermediate regime where the squeezed cat qubit is still better than the GKP qubit in respect to terms of noise. Now, how do you do gates on this system? Actually, it's very nice, because people have written papers about cat qubit gates, and we just squeeze the cat qubit. So you take any gate construction from all these results from the last 10 years, and you apply a squeezing operator from left and right to it. And instead of taking an ordinary cat with parameter alpha, you take now a bigger cat, which has exponentially in size. And why is that the reason? Why what the squeezing operator does in phase space is this compression. Take a big cat, and then you compress it along the x-axis, it just becomes flat and moves towards the origin. So that's why you want to start with a bigger size cat when you look at gate parameters. So there's this example of performing a bias-preserving Z-gate, and I will mention later what bias-preserving here means. Well, before you just have this linear drive. Now you squeeze it, you just get a parameter in front of it, as nothing happens to this Hamiltonian. But this gate parameter epsilon is also gets this parameter alpha in the denominator and the exponential parameter, so that cancels out, so nothing changes, which is very nice. Oh no. Yeah, some things moved around. So we studied this experiment numerically as well, as like just looking at the results is not enough. So what we did is we simulated this performance of the gate with a stabilized cat qubit, subject to this like dissipative stabilization, but also single photon losses as a noise source. And then there's this Hamiltonian term which introduces the gate. Ideally, you would see that you can derive analytical results for this, what you would expect, and in the plots that are these dashed lines. It matches very well, as you see. And on the first plot, we assume that there's no single photon dissipation. So on the x-axis, there's the gate time, which we increase exponentially, and this gate is actually an adiabatic gate. So the longer time we take for this gate, the better it should become, and that is true. But we also see that for any type of squeezing, the squeezed cat qubit does better than the ordinary cat qubit. If we have some type of losses, there's going to be like an optimal time, and we see that the squeezed cat qubit does the Z-gate exponentially faster and exponentially better than the ordinary cat qubit, which is a great message. If we look at the bit flip error probability, we see also that it's like still suppressed exponentially. So in that sense, it's bias preserving. While the Z error still dominates and the X error is still suppressed heavily, which is this bias preserving nature of gates. And in principle, you can do this for all the cat qubit gates, for example, for a C-NOT gate or for a Toffoli gate. And if you have all of these gates, you have a universality, for example, in this repetition code encoding. So it also allows us to do universal gate set on the cat qubit if we include state preparation to our design. So how much time do I have left? All right, great. So how do we do this in practice? This is kind of like a circuit QD sketch of what we want to do to engineer this particular dissipator of losing like 2 squeezed photons at a time. And I guess that most of the crowd is not super familiar with circuit QD, so we'll take it slow. How do we even engineer 2 photon losses? As squeezed 2 photon losses might seem very hard to do. So instead of having the operator B, we just take the operator A. And the system looks very similar. And it has a Hamiltonian, which looks super complicated, but it's not so important. It consists of like some storage mode in which we want to stabilize the cat qubit. There's some waste or buffer mode, which will dissipate photons to environment, which quickly decay. And there's a coupler, which takes care of engineering some interaction, namely this cubic interaction. And the cubic interaction is really the important step here, because what we want to engineer is this particular interaction of exchanging 2 photons from the storage mode with a single photon of the waste mode. This interaction is typically off resonance, so we need to activate it in some way. And you can like look at this thing, do some few transformations, and you see that you need to drive the coupler at a particular frequency, which corresponds to 2 times the resonator frequency, corresponding to 2 photons in the system, minus the waste frequency. So this can be done by some flux drive on the coupler, as is shown here by these gray lines. So if the resonator of the waste mode decays much faster than our cubic interaction, we can eliminate the waste mode from the system and derive some effective Hamiltonian, which then is just for the storage mode, and it will look like it was losing 2 photons at a single moment in time. Well, now basically this whole story of this talk continues. How do we go from photons to squeezed photons? Well, before we had this interaction, we apply a squeezing operator to it, and operators look a bit more complicated. This interaction will require some more terms we need to stabilize. We have seen before that we need to exchange 2 photons from the storage mode to the buffer mode. We have to do the same now as well. And we have 2 more interactions, which look a bit different. But importantly, in the end, it just corresponds to applying multiple additional flux modulations to the coupler at omega 2 and omega 3, which are a bit higher frequency and sometimes at resonant. So we get like a few more Wiggly lines here. And that's the whole picture. So any circuit that can stabilize the squeeze at ordinary cat at the moment can in principle stabilize the squeeze cat just by like modifying the drives you do to do that. So with that, I have this plot, perfect. We can go to the conclusion. This is why you always keep important plots at the end as well. It's a bit tinier than before, but well, you see that the bit flip rate for a squeezed cat or for an ordinary cat qubit reduces when we grow the cat in size. So this is parameter alpha, where when we squeeze it, it does so as well. But if we compare it at this point, for example, you gain the 6 orders of magnitude we have seen before. So that's really great. And you see that the phase flip error rate is basically constant. There's a small offset. And the reason is basically that we're comparing codes with slightly different photon numbers. So higher order terms in the dissipator will have some small effect. And we got this squeezing, so we have it like true tunable noise bias, as we have 2 separate parameters that allow us to tune phase flip rate and bit flip error rate. We have shown that we can use the squeezed cat qubit to form faster and better bias-preserving gates. And I've shown here the example of the bias-preserving Z gate. And we can do it really, really quickly in circuit QD. We just have to add a few drives, and experimentalists might not agree with this, but it's just a few drives to stabilize the squeezed cat qubit. Of course, I mentioned that there's still this open problem of, well, K will be a problem for the squeezed cat qubit. And while we argue that you could, in principle, engineer squeezed Kerr to the system to get this like combined dissipative Hamiltonian stabilization, it's going to be very hard to do, as it requires even more drives on the system. And at some point, experimentalists get angry with you. But it's, of course, a question if we can still solve this in somehow, maybe with some modified encoding. And yeah, with this, I thank you for your attention.
Great talk and for bravely ploughing through despite the problems with some of the slides there. Yeah. Can I just start off a question about the Kerr problem here? So you're saying that in some sense the slides on the left, the kind of panels on the left are showing us that if you just think about kappa 2 and kappa 1 and kappa minus, then squeezing always helps.
Yes.
You're saying that you introduce this extra problem where you have some unwanted term in the Hamiltonian.
Yes.
And it looks problematic. But if I go to the left of those plots where K over kappa 2 is very small, it looks better. There's a lower bit flip rate. So are you saying that it's problematic because you believe that actually K over kappa 2 will be large?
It's a problem of like an engineering problem. Basically, when we look at the circuit QD implementation, I was oversimplifying to just write down the cubic term, but it's a cosine expansion, or like a mixed cosine sine expansion, so where there will be more term, also quartic and whatnot. So there's always going to be Kerr, simply because we do not have these ideal cubic elements. We can engineer the flux to kind of go to a carefree point, basically, which will eliminate this quartic interaction. But if you do perturbation theory on the system, you're going to have like cubic interactions, which will still generate some effective Kerr-type nonlinearity. So you will never able be to like reduce it completely. And this is really just like the question, like, in the end, are we able to reduce this to this point where we're like left of this threshold, as I call it, where the squeezed cat qubit will perform better? And we believe so. We're not sure how far you can go left from it. But this is also kind of like cats of a small size. So I think only experiments will tell like how far we are, where we are.
Okay. But if you do the expansion of the sine term, then you can calculate what these the size of these higher order terms. And if you do that, then you end up in the regime where it's more problematic for the squeezed cat than for the unsqueezed.
Like it's kind of like you want to balance also like the higher kappa 2 is, the more nonlinearity you need in the system. So there's good chance that you get more Kerr. it's kind of this problem of finding a sweet spot.
I'm going to see if there's anyone on the app. Jake.
Thank you so much for that. I guess I had some questions regarding the implementation side.
Yes.
And so one simple question on the surface, have you checked the stability of this system under the triple drive conditions while maintaining the parameters that you need? So famously, these nonlinear oscillators, when you drive them, even though they look like they should be stable, they can become unstable. So this is known in the Matthew equation case. And I'm kind of curious how far you are, how close you are to one of these unstable boundaries when you do the triple drive.
As far as I know, like this triply driven system, well, no. No, I don't know. I think no. Like we know that there's like a phase transition going from like this phase where you stabilize the vacuum to this squeezed thing, but I don't think the triple driving is a problem. It's going to activate some additional terms which I've neglected today, but they don't seem to be problematic, like at least like from an overview.
So in a technical sense, then you're saying the Wronskian is positive.
Yeah.
Okay.
Okay. Nicholas?
Thank you for the talk and for making it accessible for people like me who don't know how to design a qubit. So how should I interpret that? Should I think that we don't need anymore to correct X errors, let's say, at the higher level of encoding? Are you convinced of that?
Am I convinced of that?
That we don't need a second level of encoding to correct both type of errors, I mean.
It kind of depends on like what is your algorithm, and of course, like at least in this like simplified picture, it is true. But what happens if you couple additional qubits for readout to it? It seems like that, for example, Alice and Bob, this startup that works on ordinary cat qubits, they are limited. They're gonna have like the bit flip error rate will level at some point, and they just cannot do it better. So just only get a bias of like maybe a factor of 1,000, and that's maybe not enough for your error rate. I think we will like have like rectangular surface codes or something like this.
You certainly need it for the phase noise.
Yes.
Phase noise is higher than normal qubits.
Yeah, I mean, I'm not sure I understand well what's happening, but if you can get rid fully of one type of error.
Yeah, we're not going to get rid fully of one.
Okay, despite the dependency that doesn't depend on your parameter R for the second type of noise, it's not enough? What is the issue?
I think there might be some experimental issues in the end that like that's actually not the ideal system we're going to implement, but there's other spurious modes and whatnot.
Okay, so in this model it will work, but you expect other issues to come up.
Yes, I think it will still be greatly beneficial, but I will not argue that you can forget about X errors. No.
Okay, thank you.
Yeah, I have to. Oh,
Go on. We've got enough time for two questions, so.
yeah, I had two short questions. I mean, one very short thing was just like you mentioned that there was a increased sensitivity to higher order nonlinearities if you squeeze the cat.
Yeah.
And I was wondering, does that grow with the order of the nonlinearity, or like is there some analytic behavior that you can extract, or is it?
Yeah, it should, because I mean you can think about it as ordinary oscillator will lead to rotations of your like harmonic oscillator will rotate in phase space, and now if you have K, you get some rotation that is dependent on the photon number, and now like any higher order Kerr in the sense will have like n square, so like it gets faster and faster. So there's going to be a problem, but these terms will be less like due to the cosine expansion. So it's kind of the question of you will find an optimal sweet spot, I guess, in the end.
So, okay, so you're imagining that there could be a trick that you can like push the
Yes.
issues like further up in the order
Yes.
of nonlinearities.
Yes.
Okay.
Last question.
Yeah, I'm curious. You consider the Kerr nonlinearity problem, and have you analyzed the effect of three photon induction for other systems? Like when you introduce ring resonator, will it be strictly bad for the code, or I know it will lead you probably outside of code space, but has anyone analyzed the effect of that?
You like this three photon interaction, the cubic interaction? I'm not sure I understand the question.
So Kerr is to the order 4, right?
Yes.
But you can also have to order 3.
Yes, but so the thing is that the order 3 typically is off resonant
Yeah.
if you do not activate it, which we're trying to avoid. So
Yeah. But what if you intentionally activated?
you're going to stabilize. Well, if you unintentionally, you're going to get a different system. You get, instead of a 2-headed cat, you get a 3-headed cat, like in some parameter regime at least. I wrote a bachelor thesis about this. No, I don't think so.
Okay, we're going to have to wrap up now. So let's thank all of the speakers in the session again.